Good morning, everyone. Welcome to the class. Today, I'm going to continue the subject on back propagation through time. It is useful to develop back propagation rule, especially in RNN and LSTM. So today, in this class, I'm going to shortly review the backpropagation through time of RNN, which was given at the last class. And in addition, I'm going to talk majorly on the backpropagation through time on LSTM. Then at the end of class, I'm going to talk about transformer learning that is also useful for natural language processing. So today's class subject has three parts. I'm gonna review the RNN backpropagation through time, and then I'm gonna demonstrate the mathematical induction process of LSTM backpropagation. At the final moment of class, I'm going to talk about transformer learning. This slide is overview of class today. Because RNN and LSTM and transformer learning, all those are useful for processing of sequential data. One of the most important application of sequential data is natural language processing. Natural language processing. Next week, I'm going to give lectures on CNN and GAN. Those AI machine learning models might be useful for processing of image, but for the natural language processing purpose, RNN and LSTM and transformer learnings are quite useful models to be used. As I draw at the bottom of the slide, we have a sequential data H1, H2, up to HT. T means terminal. And then input will be added to hidden layer with multiplication of U matrix. And this hidden layer output will be connected to output vector Y with matrix V. Because of sequential nature of this model, hidden layer H1 is fed to H2 with X2. And when H1 is added to H2, we have multiplication matrix W. And H2 is connected to H3, and so sequentially it will be connected to HT. At each output of Y, we can define cost function J. Of course, we need to know the true value Y-1, Y-2, up to Y-T, assuming this is the unsupervised learning. By comparing this Y and Y dash, we can define cost function J1. However, in this case, we have a sequential output from J1 to J2 to up to J terminal. So when we are executing the back propagation through time means we have to go through a back propagation from time step t to time step to 1. It has to go back. That is why we are calling this process as back propagation through time. And then total cost function J is summation of JT, because we have to add all this cost term. However, you remember that this cost function jt is affected by output yt, yt is affected by ht, ht is affected by h2 and h1. And each step of a transition from H to H, hidden layer to hidden layer, we have a multiplication factor W. Also, H has activation function, usually tangent hyperbolic function. When you go through backpropagation at each transition from hidden layer to hidden layer, we need to know derivative of hyperbolic tangent function. These are the overview of so at each j, t is affected by w and j2 is affected by w. So it is a little bit complicated, but effective of w is multiplied as many times as terminal number t. That is the basic conceptual view of backpropagation in RNN and LSTM. So I think this is backpropagation through time sequence. First, we know that jt is the cost function. Of course, we have to summarize all of the cost function with respect to t. T is from 1 to t. Then we have to find a path. Backpropagation path is that could be many numbers, many cases. But in this case, I'm going to give you only a few cases. Generalization could be a tedious and time-consuming work, but for the purpose of time saving, I'm not going to derive all the paths. I'm going to show you only a couple of cases. And then if we want to develop a model, new RNN model or new LSTM model or new transformer learning models in the future, you can do yourself. It takes a quite good amount of time to do that. And then develop chain rules. In order to develop chain rules, you have to know the derivatives of cost function and softmax function and activation function and also switching function. Especially in LSTM, later on, I'm going to show you there is a switching function. And in this case of LSTM, we're going to use the sigmoid function. So in order to develop chain rules, we have to know the derivative of cost functions, softmax function, activation function, and switching functions. Why do we need to do that? Because we're going to use the gradient descent method. Gradient descent method means that we need to know the slope of the function with respect to the dimension x, y, or 0, or whatever parameters. And then we repeat this sequence, then we can update the w using gradient descent equation. And this is gradient descent equation. And once we update w, then you repeat again for all paths and all w's. In these graphs, I use the scholastic representations, but actually it is W matrix and it has many ij elements. So there are a lot of iterations going on in this backpropagation through time sequences. There are smaller loops of iteration, larger loops of iterations, the bigger loop of iteration. This kind of software method is called dynamic programming. It is actually coming from computing power. So once again, I want to emphasize that the reason we are able to use this machine learning so effectively is that because of the computing power and memory power. These are the overview of back propagation through time. Through time actually coming because of the sequential nature of the input data and the sequential nature of the cost function. That is why we call it back propagation through time. So today's class has three factors. I'm going to show you the back propagation of RNN again and back propagation of LSTM again. And at this final moment of the class, I'm going to give you a short introduction of transformer learning. In transformer learning, I'm going to talk about BERT and GPT-3. More details of this BERT and GPT-3 models will be given at the middle of June. I'm going to allocate an hour of class to talk about that, but today I'm going to shortly introduce that. Now, let me briefly review the previous class. This is the back propagation through time in RNN. Let's calculate the chain rule of JT plus 1. That is the case of path 1. As I mentioned in the previous slides, we have to find all the paths to develop the chain rules. I'm going to show you some simple case. And for the case of JT plus 1 with respect W, first we have to develop a relationship with cost function J to output Y function. And usually cross entropy function will be used. And then we have the relation with the YT to output T. Is the cross entropy function. Here we use the softmax function, and the relationship between output vector and hidden vector is described by V matrix. And of course, HT plus 1 is given by a combination of previous hidden layer multiplied by W and input xt plus 1 multiplied by U. And of course, we have activation function of tangent hyperbolic activation function. And then we have to make a relationship between ht plus 1 to W. So in order to develop this chain rule of back propagation through time at jt plus 1, I call it is path 1. And then we have to find relationship 1, 2, 3, 4. If we develop those equations, we have to do the derivatives. So this is the mathematical description. We have to find the relationship between output function to the cost function with output function, relationship with the output function with the output function and the O function. And that's number 2, O function with T plus 1. And this is the derivative of the softmax function. This is the derivative of hyperbolic tangent hyperbolic function. I think this is coming from here, and the last term is coming from here, because I talked about in details last class. I'm gonna I think 1, 2 will come here, 1, 3. I think this term is coming to here. Multiplication of these two terms gives this first term. Second term is the derivative of tangent hyperbolic function. At the last term we have ht, because the derivative of 8t plus 1 with respect to omega is actually ht, that is coming to here. So with given this equation, we can update the w. And that is, and especially the 1 minus tangent hyperbolic square is described by delta t plus 1. And this is the final expression of backpropagation of path 1. That was I I gave you last class. If we move a step further, we can derive the equation, backpropagation equation of path 2. In this path 2, in the previous slide, I was talking about path 1. In this case, we only encounter this hyperbolic tangent function only once. But in path 2, we have to go through this cost function, softmax function, v. But however, we have tangent hyperbolic function twice, and w is included twice. If we go through this chain rule again, we found that we encounter a derivative of a tangent hyperbolic function twice. As I mentioned before, derivative of tangent hyperbolic function is described by this equation 1 minus tangent hyperbolic square. And then we found that in this chain rule, that is the path 2 case, that is the derivative of cost function at t plus 2 with respect to w this is the same as before, but we saw that delta is multiplied twice. So let's assume that if we want to develop a chain rule equation of JT terminal, then it has to go through all this step, and then we have to be able to calculate t plus 1, delta t plus n minus 1, and it has come to delta t plus 2, delta t plus 1, and at each time we have to multiply w. So repeatedly, with the proportional to the step number n, we multiply this delta function. That is 1 minus tangent hyperbolic function. That is less than 1 because tangent hyperbolic function square is between 1 to 0. So that actually delta means 0 to 1 because tangent hyperbolic function square is 1 to 0. So it is less than 1. So that means that if we go through all these steps of backpropagation, this derivative will all be banished. It is becoming almost 0. So effect of initial input H1 may not have so much impact at YT terminal. So because of that, it has some problem of gradient descent and W update. The effect of at the beginning of this sequence has very little impact. They don't remember what we was talking about at the beginning. So that is called vanishing problem. This is the general expression of backpropagation through time with respect to W. I'm not going to do all this rigorous induction of this equation, but because I gave you a slide overview of path 1 and path 2, you can imagine how this equation came from. Now let's move on to LSTM. The conceptual view of RNN and LSTM are very similar, and backpropagation through time sequence may be very similar. But for the purpose of clarification, I'm going to spend an hour to show you the derivation of backpropagation through time equation in LSTM. As I mentioned in the previous class, in LSTM, they have cell matrices. It goes through from previous state to next state. In RNN, it has to, previous information has to go through tangent hyperbolic function, It has to go through nonlinear function of tangent hyperbolic function. And you remember that tangent hyperbolic function is between -1 to 1. As some of edge information will be cut off. It is nonlinear. It is not nonlinear. So some information of previous state may be distorted and transmitted to the final state. But however, in LSTM case, it goes through. Just some information, new information will be added. It is non-linear process. It is just previous information is carried to next state with a large vector CT, but some information is added that is coming from previous hidden layer and current input. It has go through the tangent hyperbolic function and it will be added to the state. So naturally, LSTM has more property to remember what was told at the beginning of text or beginning of book or beginning of sequences. So it has more long-term memory. However, sometimes you want to forget what happens before. Then your input, previous hidden layer input and current input will be added and put into the sigmoid function, and it will work as a switch. If output is 1, CT, cell's state will be transmitted to the next one. If switch state is 0, it will be disconnected. This is why we call it forget gate. So sometimes if you want to forget it, that is not important to remember, to understand what is said, what is the meaning of your textbook or sequences. Sometimes this forget gate will be used. So that's why we have forget gate. Also, whether your new input will be added to your cell state, sometimes you have to determine that, and that is also being said input gate. Of course, your previous hidden layer and current input will be fed into the sigmoid function. Depending on the output of sigmoid function, it will be on or off, switched on or off. Also, your current state, CT can be transmitted to the output YT, and it will, by comparing with the true value, you can define the cost function. Little bit complicated compared to RNN, but I would say that major point of this LSTM structure is that you have a C matrix, that is the basic information carrier from beginning of your sentence to the last sentence. Sometimes it will be forgotten, sometimes it will be added with a new input of previous hidden state and X state. Now, I would like to talk about the backpropagation through time. So path, as I mentioned before, we have to find all the paths. Maybe paths. Maybe it could be 100 or 1,000. But if you develop good logics, or it can be done automatically. But I'm going to give you a few examples of backpropagation through time. Number one case, I suggest path A. In the case of path A, it comes from JT, cost function JT, YT, and hidden layer. Here we have cross entropy function, and we are involved in softmax function vector V, and that has to go through the output gate. Sometimes output is switched on and off, and that switching signal is being said OG, that is the output of the sigmoid function, and this cell state is fed into the tangent hyperbolic function. So this path has goes through this path. Cost function, output function, softmax function, V matrix, and then this switching function, and switch input is the sigmoid output function, and sigmoid output function is the function of previous hidden layer and current input. Here we have matrix W and here we have matrix W. So in order to optimize the matrix W that is connecting X to this output sigmoid function, we have to go through all these paths. In order to do that, we have to know the mathematical description of those elements. Then we will be able to do the derivatives. And first one is the, I would say, output gate will be used in path 1. Output gate output, this output gate output will control the switching of this one, this output switch. And it is the function of sigmoid function. Input is the previous hidden layer. That constant is called WOH output and hidden layer. And the current state of XT, that connection is the matrix W O X. O means the output switching and X is the X input. And hidden layer output is the multiplication of this gate switching and tangent hyperbolic function. And HT, hidden layer, CT, C-T, CT is the function of previous cell state T-1 multiplied by forget gate, and the C-T, this here is the output is C-T, okay. I'm gonna go back again. For example, let's explain this function. CT, this CT is the addition of previous previous cell state multiplied by sigmoid function. And here, CT, cell state, next cell state is the previous cell state multiplied by forget gate, and the previous input of cell state multiplied by input state. So these are the mathematical description of all these structures. This is the graphical description of LSTM, and this is the mathematical description of LSTM with respect to input gate, forget gate, output gate, and C dash, and cell state and hidden state. I'm going to use these equations when we are driving these backpropagation equations. Of course, during the backpropagation and training, we're gonna update all these matrices. W is being used for input gate, W is used for forget gate, W is used for output gate, and W is used for cell gate. So in the case of path A, we have to define a cost function derivative with the YT output. And this is the cross entropy. This is the softmax function. And this is V matrix. And so the last term is the hidden layer output is the tangent hyperbolic function of cell state multiplied by the switching gate. Let's go back. This hidden layer output is the multiplication of output gate, that is sigmoid function, with the tangent hyperbolic function of cell state. There are two input. One is the tangent hyperbolic of cell state, and second input is the output gate sigmoid function. That is exactly this term. And with respect to the, in here, I'm gonna make a relationship with W. In that purpose, tangent hyperbolic function is a kind of constant. So we don't need to worry about the derivative. So tangent hyperbolic of cell state is the constant. Now we have to make a derivative of the second term, sigmoid term that has an input of W WOH and previous hidden layer function, WOX multiplied by present input function and bias. And derivative of sigmoid function is itself and 1 minus itself that we spend quite amount of time at the beginning of class. The sigmoid function derivative can be described by this equation. Last term is the derivative of this one with respect to the HO, and then HT minus 1 will come out. That is the freshman college level mathematics. Then we finally got this chain rule equation. So now, again, this is the summary of derivative chain rule for gradient descent. It will be fitted into up here, and it will summarize from at the beginning of the sequence to the final sequence. Then you can keep update. And it has the 4 different terms. First term is the derivative of cross entropy function. Second, the term is coming from softmax function. Third term is making connection between Y to off output function. And this is the cell state at STM. You remember that all the information is carried by CT, that we have to apply the tangent hyperbolic function. Then this is the derivative of sigmoid. Actually, it is coming from output switch. That is the essential part of the LSTM. And then finally, previous input or previous hidden layer. So here only I consider a case of this path. I said this is path 1. But you have to find all the path, maybe 100 different paths to be able to find update equation of W. If you have 10 to 6 vector elements, this is the really large amount of computations. That's why we need GPU and parallel computing powers. If we do this computing in serially, it takes long hours. But if we do that parallelly, it will be much faster. For example, if you have GPU that has a calculation element that can do this calculation in parallel, and the unit element of calculation is, let's assume 10 to 6, it can be done in a second or in a minute. That is the power of parallel computing. That's why GPU is important part of the computation of machine learning, including LSTM. Now let's think about another path is a little bit different. Path 2, path B. It will start with the cost function. It will be connected to output function, and it will be connected to hidden layer function. And this hidden layer function has input of cell state. Cell state is input to the hidden layer, goes through the tangent hyperbolic function and switching function. And this cell state input is switched by output gate. That is the, so current state of HT minus 1 and HT has an effect of sigmoid function, and it will be multiplied to the cost function, the cell state function. And also current state of HT minus 1 and XT will have effect of output gate. So there are many paths to paths, but I'm going to only think about path B. When hidden layer, previous hidden layer and current input will be input to the sigmoid function, there will be also a constant W that will be updated during the backpropagation. I'm going to talk about how to develop chain rule equation to update W, and that is the case of path B. And again, I was able to derive this equation. We have 1, 2, 3, 4 step, probably number 1, number 2, number 3, number 4, or number 5, or something like that. At each step of transition, we have to do the derivation, number 1, number 2, number 3, number 4. And number 1 is the soft derivative of cross entropy function. Number 2 is the derivative of soft function. Number 3 might be the constant v. And let's pay only attention to number 4. Hidden layer output is a function of output gate with a tangent hyperbolic function of cell state. And because of with respect to the WFX, this is forget gate. Output gate has no direct input, so OG can be regarded as a constant. So only our attention will be the derivative of tangent hyperbolic function, and inside tangent hyperbolic function there is an input of the forget gate. In the forget gate there is a constant WFX. So during this process, we have should be added to the tangent hyperbolic function derivative is 1 minus tangent hyperbolic derivative function, and Ct minus 1 is the constant, and we have to make a derivative of the sigmoid function, that is f1 minus f, and finally derivative of this term inside of sigmoid function, then this xt will come out. This is very short and fast explanation of this chain rule, but if you are good in mathematics of partial derivatives, and you can follow very easily. So this is the final equation. And so if you know, for the case of path B, you can find this equation, and then you can apply the gradient descent equation. And with the given WFX and with the given XT, CT minus 1, HT minus 1, and all this information, if you feed this information, these values in this equation, you can calculate this gradient, and you can feed that into this equation. You can keep update. Yeah, let's come back to this slide, which was used at the beginning of class. This is the method of my lecture. At the beginning, I give you overview, and during the class, I give you details, and then I came back to the final slide of the class to give you the overview of again. What is the meaning of back propagation through time? In order to derive gradient descent equation, we have to calculate cost function at the final state t. And in order to make a relationship between W, some weight matrix at the beginning of state, you have to go through all these sequences, and you have to develop all the equations and derivatives to make a gradient descent equation. That is why we call it that is back propagation through time. And so these are the whether it is a RNN or LSTM, it will be the same. We define the cost function at each state, and we have to find the all paths of back propagation through time, and we have to develop the chain rule. When you are developing the chain rule, you should be able to derive equations to express derivatives of cost functions, softmax function, activation function, and switching functions, and so on. And then you update W and repeat all the paths and repeat all the weight parameters. And I think that there are a lot of iteration during that process. Yeah, this is the overview of backpropagation. This is the end of the class of backpropagation through time. I'm gonna put these slides to the teaching assistants. You can copy these equations and you can spend your time to do that, to derive all these equations. Sometimes you need to do that, or you can watch the YouTube to do that. So, but as far as you can remember this last slide of this class, I think you will be okay. Sometimes if you want to be more confident on your model, I would suggest you spend some time to derive these equations to be more confident on what you are doing, even though you are using PyTorch or TensorFlow. This is the end of backpropagation through time. Let's move on to the transformer learning. Let's continue my class. This is another view of LSTM. Let's assume that you have an input. What is your name? That input will be the sequential input of LSTM, and that is transmitted to English and another network LSTM. And let's assume that you or LSTM output is my name is John. In those cases, this information of question and will be carried through cell matrix CT. In the previous slides, we feel that cell is a small information, but cell could be million by million size matrix or billion by billion size matrix, large size matrix. So the first questioning part of LSTM could be generating the function of this part is generating the cell state CT, and CT is transmitted to second part of LSTM, and they interpret CD and they produce the sequential output. My name is John. And the first part of LSTM network could be encoder. In Natural Language Processing Society, they are saying this first part of the LSTM is called encoder. And the second part of the second part is called decoder. So encoder's function is compression of data into cell state, and it is a kind of feature extraction. We don't know exactly what is going on in cell state matrix, but we are sure that it has some feature. Compressed feature is included in CT. In decoder, interpret CT to generate my name is John, that kind of sequence. So in Natural Language Processing Society, they usually say the first part of that is encoder and second part is the encoder. The function of encoder is questioning, and second part of the decoder is answering machine. So the function of encoder is feature extraction, and second part is the data generation. The link between encoder and decoder is cell matrix. That is another view of LSTM. Now, because this is the sequential data, okay, compared to RNN, we have cell state CT, so that is good. It can remember, we can avoid the vanishing problem, so it has long-term memory. But still, the question is that it is a sequential process. Sequential process, and it takes time. Also, you remember that in LSTM, in backpropagation, we have a delta t function was multiplied many times. Delta t is the derivative of tangent hyperbolic function. It is also between 0 to 1. So still, it has some context or feature of at the beginning of this sequence may be forgotten. And so to avoid that kind of limitation of LSTM, attention network is added. That is a new wording. And if you have a sequential network with the attention network together, that is called transformer learning. If you have a sequential data, but you have all this the sequential computational time problem, and also there are still memory losing problem. So you added attention network, and that is very useful for natural language processing. And that network is called transformer learning. And recently, if you look into the website to talk about natural processing language, there are two famous models. One is the BERT model, second is GPT-3. And GPT-3 and BERT model is based on transformer learning. So I would say, considering the development stages of natural language processing, the first model is RNN, second model is LSTM. Now people are using transformer learning, and in 2020 and 2021. Right now it is going on. But as I mentioned before, LSTM also has large amount of data and sequential computations. And during the backpropagation, there are thousands of paths to develop the chain rules. In addition to those networks, we have to add attention network. So transformer learning is asking even more and more computing power and memory power. That is why GPU price is going up and going up. So this is my own graphical description of transformer learning. In the transformer learning, additional network is added that is called multi-level attention network. The key feature of transformer learning is that we have to add a multi-level attention network. In LSTM, our questioning is transmitted to the encoder is connected to decoder using cell matrix, cell T matrix. However, still, my question, what is your name? The answer is my name is John, but it's very simple 4-word sentence. But sometimes if you look in encyclopedia, there could be million or billion wording in sequential. So attention network is that if you have an answer, my name is John, these are connected to at each state from T1 to T. At each cell, each unit state is connected to output, my name is John. And depending on different features, it is a multi-level, single level. It is not single level connection. There are multiple level connections. In terms of mathematics, it could be tensor, 3-dimensional or 4-dimensional or 5-dimensional matrices. So more connectivity and more information is added in this additional connection. So encoder-decoder connection could be kind of serial connection, but this is a kind of parallel connection. Parallel connection. So I would say in transformer learning, we have a serial connection and the parallel connection together is a kind of hybrid connection. Because of direct connection from input state to the output state, the context, the meaning of sentence or wording is well carried to output. This is called multi-level. This connection is called multi-level attention. If you have sequential model that include multi-level attention, it takes a lot of computing power and memory. That is called transformer learning. That is my own interpretation of transformer learning. So in other graphical description, this is other graphical description. It has encoder has the we have decoder. Also, encoder itself has the attention network, and decoder itself has the attention network. And also connection between transformer encoder to transformer encoder, it also has attention network. I think many multi-level attention network is added in LSTM, and that is, I think, called definition of transformer network. It is good for parallel processing, so it is very fast. It has long-term connection, so it can keep a context. So this computer model is much more, this capability of this natural processing language and machine model, learning model, called as transformer learning, has more natural capability to use our language. It is more closer to our human being. Cost of this transformer learning is that connectivity and computational power and memory. So only a few companies who has large size of computers and memory can do that. Also developing all these mathematics and codings and program in order to conduct this transformer learning for natural processing language, we need probably 1,000 engineers to do that. So it is a little bit dark part of the machine learning. So you remember that BRT is the very famous natural language processing model. The name of that comes from bidirectional encoder representation of transformer. This actually T is coming from transformer. BRT only is a machine learning for encoder. As I mentioned, that it has encoder part and decoder part, and BRT is only they made developed on nature using the multi-level attention that is called transformer, but only apply the encoder. However, GPT is the generation of pre-trained transformer, and the GPT-3 has the encoder and decoder all together. So in the case of BRT, they use the training only for encoder, but in GPT-3, they train this transformer network for both encoder and decoder. These are the summary of my presentation today. And the BRT was introduced in 2018. GPT-3 is introduced last year. So these are the very recent and current researches on machine learning models. This is the end of class today. I'm sure that it is the level of class and mathematics and speed of class is a little bit higher than previous classes, especially before the midterm. But I'm sure that because we keep going on, you understand most of the terminology. So we add one step further. And I think especially in GAN and reinforcement learning will be on next level. More and more complicated concepts will be introduced and more mathematics will be added. So, but the final state of our machine learning is combining this transformer learning with the reinforcement learning. And also we have to apply them to real practical problems such as engineering problem. In our laboratory, we want to apply that for semiconductor circuit design and interconnection design. That is another difficult part of engineering. So this is the really summit peak point of, I have to say, this is the really peak point of machine learning mountain. I think we are now in the middle of that. So this is less 8,000 meter mountain. I think we started from 0 meters at the beginning of this class. Right now I'm saying we are at this height. And some years ago, I went to Machu Picchu in the Andes Mountains, and the height was about 4,000 meters. And we need the oxygen mask when we landed at the airport. You need oxygen right now, but in a day, we really enjoy the mountains. And so be patient, let's go up to that. Up to the top of the mountain, I would want to achieve 3 different areas. One is the deep learning and reinforcement, probably transformer learning and reinforcement learning and engineering. By combining them to do that, and that is really challenging but achievable targets. And that is what will going on. I think this kind of research will go on from 2020 to 2030. And really, the researchers are at the beginning stage. Let's be patient and enjoy a little bit and go to this top of the mountain at the end of June. Thank you for your kind of attention and see you next week. Next week, I'm going to go to the CNN and backpropagation CNN. CNN is a little bit easier than RNN and transformer learning. And then after New Children's Day, and we're gonna go to the GAN and reinforcement learning. Thank you. See you then. Bye-bye.